Afternoon, students. Today's topic is defects in crystal system. Now, whatever we have learnt till date, that is the crystal system, Bravis lattice in the crystal system, gaps in Bravis lattice, then Miller indices. Uh, Now, whatever we have learned, that is actually considering that our crystal system or assuming the crystal system is ideal crystal system. But whenever we are talking about the crystal system, there should be present some defects. That means there will be no crystal system that can be ideal. Every crystal system should have some imperfection. So today we are going to discuss about the whatever the imperfection present in that crystal system. So perfect order does not exist throughout a crystalline material on an atomic scale. All crystalline material contains large number of various defects or imperfections. Defects or imperfections influence properties such as mechanical, electrical, magnetic, etc. Now, there are in the category of dimension, so there are three types of defects. The major category is three types of defects are there. Zero dimensional defects, it is called point defects. One dimensional defect, it is called line defect, and two dimensional defect, it is called surface defects. So one by one we will going to discuss. Now come to the next slide. So in the category of the point defects, there are two types of defects, majorly two types of defects. That is for ionic crystal and non-ionic crystals. For non-ionic crystals, there is vacancies and the impurities atom. That can be again two types, substitutional and interstitial. And for ionic crystals, there can be again two types. It is called Schottky defect and Frenkel defect. And in the category of line defects, there is a edge dislocation, screw dislocation, and in the edge dislocation, there are again two types, that is called half plane and slip plane. And in the category of area or the planar defect or two-dimensional defect, there is a grain boundary, twine boundary, and stacking fault. So come to the first. This is the, as I told you that there are point defects can be two types for non-ionic and ionic crystals. For non-ionic, it is vacancy or interstitial, and for ionic, it is a Frenkel and Schottky. So let's discuss about the vacancy. What is vacancy? Now you can see here in the picture that there is a regular atoms are there, whatever the black color atoms are shown here. Now inside that atom there is one atom is missing, and that is identified by a dotted circle. So the missing of the atom is called nothing but the vacancy. So this missing can be happens due to the higher if you uh, heat the material when the temperature is sufficiently high, as then what will happen, the atoms are vibrate around their regular positions. Now if any atom site or any atom acquire enough energy to break the bond and leave completely the site, then the vacancy is created. So when regular atom leaves its regular sites, then the vacancy is created. Now this vacancy is actually thermodynamically stable. Now what if vacancy, if whenever if it can be said that if an atom is missing there, then how it can be stable? So this is actually nothing but the thermodynamically stable. The atom can be situated some another place. Okay. So atom cannot be go beyond its lattice. It sits some another place. So there is a vacancy is created. So that's why it is called vacancy. So we can calculate the number of vacancies, how much equivalent number of vacancy can be created for a particular one at lattice. So this is the equations for the calculation. So NV equals to N exp minus QV by KT, where NV is the equilibrium number of vacancies per cubic meter, N is the total number of sites per cubic meter, QV is the activation energy required to create vacancy. Now, as I told you, to break the bond, whenever the vacancy is created, definitely that atom have to break the four bonds from its regular site. So to break this four bond, it needs some higher energy. So that energy is actually called as a activation energy, and that can be found by heating the temperature, by gaining the temperature. Okay, and K is the Boltzmann's constant and T is the absolute temperature. So one numerical is given to you, one that is calculate the equilibrium number of vacancies per cubic meter for copper at 1100 degrees centigrade. The energy for the vacancy formation is zero point 0.9 electron volt per atom, and the atom weight and the density is of the copper is 63.5 gram per mole and 8.4 gram per centimeter cube. And K is the Boltzmann constant, which is the value is given here. So if you put the just status in the previous equations, what will happen? You will get the equilibrium number of vacancies almost present per cubic meter, and only you have to just maintain the units. Okay. And the answer will come 4.0 into 10 to the power 25 vacancies per meter. Now come to the next defect, that is interstitial. So that is actually mainly due to the impurities. So impurities can be present in the interstitial positions, that means interstitial void positions, or it can be substitute the mother atom. Okay. So when the impurities present inside the void portion of the regular atom, so this type of impurities, this type of defect is called actually interstitial defect. So you can see here, so there is a regular atom is there. So these are the black color atoms shown here, and another red is nothing but the impurities, where red is inside the void portion. So always whenever we are talking about the interstitial defect, so definitely your whatever the impurities, that should be much lesser radius than the mother atom. Okay, because it's actually seated on the interstitial void position. So void radius should be always less than the atoms. So that's why it is that main criteria, major criteria for this type of defect is your impurities radius should be much less than your mother atom. Next, come to the next one, that is substitutional defect. Substitutional defect, you can see here that the impurities radius and the mother atom radius, that will be same, nearly same, so that impurities atom can replace that mother atom. Okay. So this type of defect is called substitutional defect. So it is refers to a foreign atom that substitutes for or replaces the parent atom in the crystal. Now the example is that if the pentavalent or trivalent impurities atom doped in silicon or germanium are also substitutional impurities in the crystal. Now these are the point defects, impurities, that is interstitial or substitutional, whatever we are talking about these things. So these are actually in the category of the non-ionic crystals. So when you are talking about the ionic crystals, that means ionic crystal means NaCl, ZnS, cesium chloride, zinc sulfate, So these are actually nothing but the ionic crystal. So that means there should be one cation, another should be anion. So always when you are talking about the cation anion, so cation radius is always less than the anion radius, because cation is the electron donor and the anion is the electron acceptor. So when it donates the electron, automatically its orbit becomes lesser, orbit number becomes lesser, and whenever there is an acceptor, so its orbit becomes more. Okay, so that's why the radius of the anion is much larger than the cation. So you can see here the one structure is given to you. So that is the black color is anion and the red color is cation. So for this type of ionic solids, there can be two types of defects. One is called Frenkel defect. Frenkel defect. What is Frenkel defect? If the cation move from its regular site to another site, from its regular interstitial site to another interstitial position. So this type of defect is called Frenkel defect. And another one is Schottky defect is nothing but there should be missing of two. That means anion and cation. If both will be missing from the site, from the regular atom site, then this type of defect is called Schottky defect. So only when the cation is moved from its original position to the another interstitial position, so then it is called Frenkel defect. And when both are missing, that is anion and cation both are missing, then this type of defect is called Schottky defect. Okay, good afternoon, students. So in the previous lecture, we have discussed about the point defects. Now this is the continuation part of these defects. Now this is the line defects. This is nothing but the one-dimensional defect, line defects. So line defects can be segregated in two categories. One is edge dislocation, another one is screw dislocation. Again, edge dislocation can be divided into two uh, uh, part, that is half plane and the slip plane. Now there is okay, we go to the discuss about the half plane and safe plane. Then we will go to the this B. This B is actually called as a Berger vector. That is actually nothing but the magnitude measurement of the magnitude and the direction of the distortion. Lattice distortion. Magnitude and the direction of the lattice distortion. Now for edge dislocations, always the Berger vector is normal to the dislocation line, and for screw dislocation, Berger vector is always parallel to the screw dislocation line. Okay. Now come to the first, that is edge dislocation half plane. So why it is called half plane? First going to discuss about these things. Now you can see here in this picture, just left side picture, there is a perfect crystals are there. That means each lattice point there is one, each atoms are present. So this is the 2D structure is given to you, and if you imagine it's in the 3D structure, so there it will be each lattice point is there, and each lattice point contains one atom, and each atoms are separated one lattice parameters, that is A. Now somehow in the middle picture you can see here that in between the first three rows there is no defects is present. That means all the crystals are perfect, all the atoms are perfectly arranged in the each and every lattice point. But if you go for the lower part, then you can see there are missing of atoms, this here, this and here and here. So the missing atoms are 3 points. There are three lattice points are there where the atoms are missing, and the distance between one atom to another atom is 2a due to the missing of the atom. But in the basic instinct, uh, the all the atoms are tries to gain its original position and try to gain its original lattice parameter, that is A. So what will happen? The lower portion atoms, they are tries to come each other. So there is a the upper portion you can see here, the rightmost side, rightmost side picture you can see here. So the upper portion, a funnel type shape is present, funnel type distortion is present, and the above portion there is a compression zone, and the lower portion there is a tension zone. And another thing is, the whatever the point is missing, whatever, then what will happen, they will gain the same structure again. So the defects is happens only at the half plane. The upper portion, if you see, there is a no defects. If you see the lower portion, lower half plane, then you can see there is a defect. So that's why it is called half plane edge dislocation. Now come to the why it is called 1D, because if you think about in a 3D direction, it is a structure, it is a whatever the image is shown to you, that is 2D. Now if you consider the 3D, so what will happen, that the atom where the missing atom is there, and that atom will be missing throughout this backside of the board, okay, throughout the backside of the board, and it will be continued to the infinity. So whatever the diameter of this distortion, that can be very very negligible than the length of the distortion. So that's why it is called line defect. So it's the defects happens throughout this line, along the line. So that's why it is called line defect. And as it happens at the one half of the one half plane, so then it is called half plane edge dislocation line. So here you can see that D is much less than L, so that's why it is called as a 1D dislocation. Okay, edge dislocation is nothing but a 1D. So this type of distortion is called half plane distortion. So here you can see this is the perfect crystal, and there is a defect crystal. So there is a missing of some atoms are there, and this is the defect crystals. The strength and the ductility of the metals are controlled by this distribution. So this is the strength and ductility. If there is a defect is there, the strength and ductility will be differ from material to material. So this is the, you can see here some small lines are there. This is a same picture of a material. So here whatever the line you can see, these are actually nothing but the edge dislocation line. Mhm. Now, as I told you, that is the Barger vector is nothing but the gives you the magnitude and the direction of the distortion. So you can see here initially, if you consider the middle picture, so initially it starts from the P, the perfect crystal initially starts from the P, it goes to the upward, then go to the right side, then bottom, and then left. So there is a perfect crystal, so it gives a square, perfect square it gives. And if you go to the next, the distortion portion is there, distortion crystals. So it starts from the P and goes upward again towards the right side, then goes bottom and it goes to the point Q. So the distortion amount is nothing but the towards this right side. Barger vector is towards the right side distortion from Q to P, and the amount of the distortion is nothing but the lattice parameter A. So that's why B is called actually nothing but the it helps to determine the direction and the magnitude of the distortion. Come to the next part, that is called slip plane. Slip plane is actually nothing but the cutting of the plane. Suppose there is a perfect plane is there. So you can see here 1 to 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there is a 9 planes are there and suppose and assume that each plane contains this type of atoms, and so that it becomes a lattice. If you consider, if you imagine this thing, it gives you nothing but the perfect crystal or lattice. Now if you cut as shown in the picture, if you cut it and slide that plane from one to 2 and 2 to 3, so what will happen initially? So one plane is matched with the 2 plane, 2 plane will be matched with the 3 plane, 3 plane will match with the 4 plane, and the cutting portion is happens up to plane 4. From 5 onwards, you can see it will be same, it will be perfect system. So the cutting, the defect is happens up to 4 plane. So when 3 will matches with the 4, 4 has no plane to which it can be matched. Okay, so 4 plane is hanging, there is a no at the bottom side there is a no matching plane. So whatever the plane is there, so it becomes a it creates a distortion. Okay, so that also you can see here the throughout this plane, and it goes towards the back side of the board or back side of the LED screen. You can see here that this line, towards this line, the all the throughout the infinitive line, the distortion is happening. Again, as the diameter is very low, much low than the length of the distortion, so that's why it is called line defects. And as it happens by cutting the plane, by slipping the plane, by sliding the plane, so that's why it is called slip plane. So you can see there, you can see here one plane when a the what are the plane is shown here by the pink color plane is shown here. So one, the left side plane is slip plane and the right side plane is no slip plane. Okay. So here in that case you can see here the distortion happens towards the Berger vector this side, towards the left to right, but the um, tangent vector is nothing but towards the from bottom to upward. Okay, so always B is normal to the dislocation line. So this is actually nothing but the dislocation line. So always Berger factor is normal to the dislocation line in case of edge dislocation. Okay, now come to the screw dislocation. So this okay, this is the edge dislocation case. There is a another energy is elastic energy is given to you for compression and tension zone. So that is given by half G into B square, where B is the Berger vector and G is the shear modulus. Now another one is screw dislocation. Screw dislocation is nothing but if you there is a perfect crystal is there, and if you press this one plane towards the bottom, so what will happen? The one plane, this side, the right hand side plane goes down one lattice parameter down. So what will happen? There will be a continuous. So you can see here that one plane, uh, first one is the second plane is matches with the first plane, third plane is matches with the second plane, fourth plane is matches with the third plane. So like this way, if as the screw is rotate, you can as the screw is rotate, you can see here the rotation is continually like this. So that's why it is called the screw dislocation, and Berger vector is towards the dislocation line. So always this side is Berger distortion Berger vector, and dislocation line is also this side. Okay, you can see here dislocation line is this side and Berger vector is also this side. So that's why for screw dislocation, P is always parallel to the dislocation line. Now come to the surface defects. So this is called actually grain boundary. Grain boundary is one of another type of defect that is called surface defects. This is actually nothing but the polycrystalline material. When there you can if we when you can see that there is a polycrystalline material. So first, if you uh, phase transformation is done from liquid phase to solid phase, so what will happen? Initially few nucleus is created, then that nucleus is gradually grow, and what will happen, this one nucleus another nucleus, they are impinged with each other, and in between then there is a uh, boundary is created. Okay, so that type of boundary is called grain boundary. So here you can see one lattice, another is this side is another lattice, and in between these two lattice there is a grain boundary is created. So this type of defect is called grain boundary, and each and every crystal system there should present some grain boundary, because without grain boundary the polycrystalline material is not never happens. Okay, so every crystal system that these defects must be present. Now grain boundary can be two types. One is tilt boundary, another is twist boundary. You can see here the picture. Tilt boundary means the angle between the lattice arrangement. Okay, here the red color and the blue color, they are actually a little bit aligned. Okay, so and that the uh, degree of alignation you can see here, the theta by 2 and theta by 2. So this type of tilting is happens, so that's why it is called tilt boundary. And twist is nothing but one plane is seated in the another plane. One lattice is one grain is seated on the another grain, and they are twisting each other with the theta angle. So here you can see here theta angle. So that's why this type of boundary is layer is called twist boundary. Always the rotational axis, this is the rotational axis and this is the grain boundary axis. So in case of tilt boundary, always the rotational axis is parallel to the grain boundary, or in case of in case of twist boundary, the rotational axis is normal to the grain boundary. Now come to the twain boundary. Twain boundary is nothing but sometimes it is called mirror boundary. So there should be perfect region. Another left side is perfect region, right side is perfect region, and in between there is a two lines are there. So there these two lines is actually called twine planes or twine boundaries, and twine boundaries never happens alone. There should be two lines, definitely always there should be two lines, because once there will be perfect crystal and after mirror effect there will be another perfect crystal it will come. So always there should be two boundaries should be present. So this type of uh, uh, defect is called twine boundary. So this is the same picture is given to you. Now you can see here all the there is lots of two lines. You can see here lots of two lines. So these are actually nothing but the twine boundary. Now come to the next part that is called stacking fault. So this is the end of the defect. So this is called stacking fault. Stacking fault means suppose we know that the stacking arrangement for the uh, CCP structure. CCP structure is ABC. When I say the arrangement of the CCP structure is ABC, ABC, ABC. So this is the perfect CCP structure is given towards the A in the picture shown in picture A. But what happens if there is a tendency of A to sit it on B or C? Same. Okay, so when B and C planes are or B and C planes are atomic atoms are equivalent with each other, some properties are same, so what will happen, A will get confused on which it can sit. Either it can be sit on B or it can be sit on C. So A will get confused, and by this confusion sometimes it happens A is seated on B instead of seated of C on C. So in that case this type of stacking is this type of fault is happens. So this type of fault is called stacking fault, and that is due to happens the equivalency nature of B and C. Okay, so this type of stacking fault is called this type of defect is called stacking fault. So, students, so this is all about explaining the defects, what happens in normally in the crystal systems. So, in the next class, we'll discuss about the another topic, phase transformation. Thank you.